there's an assumption that that's true. So in other words, for today, we have to make the definition true, right? But we're missing a place. We're missing A, right? So we have to figure out what goes in A's spot that would make the definition of continuity true. Okay? All right, that's what we have to do. That's the difference. In the previous example, we were just checking to see if it was continuous. Now what we have to do is a little bit different. It is continuous, but we just have to figure out which value goes in A to make it continuous, right? Okay, so first thing we have to do is decide 4A. Where's the only place that 4A could have issues with continuity? At 1, right? That's where it switches. At 1 is where it switches what it does, the equation, right? So 1 is the only place we need to check. So what I'm going to do is I'm going to set this up over here, the definition for 1. Okay? So let me write that down. So we're going to say the limit as x approaches 1 from the left for g of x has to equal the limit as x approaches 1 from the right for g of x. That also has to be equal to the overall limit at 1 and the answer at 1, the y value at 1. Right, limits are approaching. G of 1 means what's the answer at 1? Where is the dot when x equals 1? Okay, so what we're going to do now is we are going to answer these as best as we can right now. Okay, so the first one, the limit as x approaches 1 from the left. Which one would we use, the top or the bottom? The bottom, right? The bottom. So what did I do last time? What did I do for the letter C right above it when I wanted to check from the left? What did I do? How did I check continuity from the left? What was the process? I plugged in the value in for x, right? That's what I'm going to do now. I'm going to plug in 1 for x here. When I plug in 1 for x, I get 1 plus a. I don't know what a is. That's what I'm trying to figure out. So it just leaves 1 plus a. Okay. Okay, so now let's do the same thing for the right. So if I'm coming from the positive side, which equation am I going to use, top or bottom? Top. Same thing. I'm plugging in 1 for x. I get 8. Let me highlight these. Okay. Let's keep going. The overall limit needs to be the same. It needs to be the same because it says it has to be continuous. So this question says it has to be continuous for all real numbers. So that number here, we don't know, but it has to be the same as both green guys. Okay. G of 1. How would I figure out G of 1? Plug it into the top, right? Because that's where it's equal. I did that earlier, right? So the answer is 8. So for this to be continuous, all of those guys, all of those green guys have to be exactly the same. 2 of them are, right? 2 of them are. 2 of them are 8. But 1 of them is not. So what we're going to do is we're going to set them equal because they have to be equal, right? So 1 plus a has to be equal to 8, right? So what does a have to be to make it 8? There you go. If a is 7, they're all equal. If a is 7, they're all equal. And then this one will become 8 as well. Right? So the only value for a that would make it continuous everywhere is 7. Okay. Let's do letter B now. Letter B is exactly the same, except instead of less than or greater than, it's just not equal to. Okay. So letter B, where is the only place this h of x could have issues with continuity? At 1, right? It's not always 1. I know number one, A and B are 1, but it's not always going to be 1. But for these two, it is. So let's set it up. The limit as x approaches 1 from the left for h of x has to be equal to the limit as x approaches 1 from the right for h of x, which is equal to the overall limit, which is equal to h of 1. All of those have to be true. Okay, so what we're going to do is we're going to do our best to figure them out. Okay. Let's do the first one. The limit as x approaches 1 from the left. Which one am I going to use for that one? The top or the bottom? As it approaches 1, not at 1. So as I approach 1 from the left side, because that's what a limit does, approaches it, right? So as I'm approaching 1 from the left side, which one am I going to use, the top or the bottom? Top. I'm going to use the top because the top isn't at 1. The bottom is at 1. That's the only place it's at. It's at 1. Well, limits don't exist there. They're approaching. So I'm going to use the top. Okay. So I plug in 1. And I get 0 over 0. What do we know about limits? And when we plug in and we get 0 over 0, what does that mean? There's something else we have to do. Factor, right? It's kind of like, let me go back a few. When we first did, what happens if you plug in a number? Plug in a number you're done, right? If you plug in a value for a limit and you get a number, you're done. What happens if you get 0 over 0? Well, you're not done, right? We have to do one of these things. Factor, reduce, rationalize, one of those things, right? We're not quite done. It means there's work still left to be done. Okay, so let's look at this guy up here. X to the 4th minus 1 over x minus 1. Kind of taking a pause before we go back. Well, the top is a binomial. The bottom is a binomial. So maybe factoring will help. There's no square roots. There's no like trig. There's no cosine, sine. There's nothing like that. So I'm thinking the only thing, we have one fraction, is factoring. So can I factor the top? So it's a binomial. The top is a binomial, right? It's difference of squares. Yeah. I know it's x to the 4th, but it is difference of squares. It's x squared minus 1 squared. So in other words, it's x squared minus 1 over x squared plus 1. And it's still difference of squares, right? One of them is still difference of squares. The first one, I can break the first one down to x plus 1, x minus 1. And then the second one is not difference of squares, so it stays. So the top I can factor. Bottom I can't factor. It's not difference of squares. Close. If it had a squared, it'd be difference of squares, but it doesn't. So this guy just takes a straight path over here. Now something's going to cancel out, right? So what I'm left with is no more denominator, or it's just 1 on the denominator, right? And I have x plus 1, x squared plus 1. That's what I'm going to plug it into. That's what I'm going to plug it into. I'm going to plug in, I'm going to change the top. The top is no longer x to the 4th minus 1 over x minus 1. It can be reduced. It can be factored. So I'm going to, this guy is no longer, this is the guy I'm going to use. Okay, it's the reduced version of it. It's like a fraction that's reduced. They're the same fraction, but one's reduced and one's not. Okay, so let me try this again. Let me try step 1. Let me try the first step again. I'm going to plug in 1 to the top. But the top is no longer what it was. The top is actually this guy over here. So I get 1 plus 1, 1 squared plus 1 over 1, which is 2 times 2, which is 4. Okay. Done with that one. How do I find the limit as x approaches 1 from the right? I use the same one, right? Don't I use the same exact thing? So instead of having to plug it in again, we know the answer. It's just 4. And by rule, if those two guys are the same, then the third one has to be the same. Now, how do I find h of 1? This is where I plug it into the bottom one. Where x is 1. That's the bottom. X equals 1. Well, we don't know that. That's just a. I can't plug in 1 there because there's no x. So it's just a. So what does a have to be to make them all true? 4. A is 4. And you're done. So for this guy to be continuous, has to be true. A has to be 4. Okay. See, we're all here. We're all here. Okay. Okay, so now let's go to letter C. Letter C is exactly the same as what we're doing. The difference is it's got 3 pieces instead of 1. That's just that's the difference. Okay? So our directions are the same. Anything that's not an X, you got to figure out what it is. Well, we don't just have an A, right? We have an A and a B. So we got to figure out what A and B are. Okay? So where should we check? Looking at this guy, where should we check for continuity? Where might we be concerned about continuity? At 1. Definitely 1, because they switch at 1, right? They go from the top to the middle at 1. Anywhere else? And also 2. So we got to check in 2 spots. Okay, so let's start with 1. As x approaches 1 from the right for f of x equals the overall limit and then f of 1. Okay, so I set up the definition. So if I want to check the limit as x approaches 1 from the left, which piece am I going to use? X plus 1, ax plus b, or 3x? Yeah, x plus 1 because that's the one less than 1. Coming from the left is less than 1. So I'm going to plug in 1 here. And I get 2. Okay, so we get 1 answer. We got 2. If I'm checking x, if I'm checking as x approaches 1 from the right side, where should I plug it into? The middle, yeah, the middle. The middle because that's where x is approaching 1 from the other side. So I plug it in. I plug in 1 for x, and I get a plus b. Don't know what they are, but that's what I get. The overall limit, well, we don't know that because those 2 guys have to be the same. Those 2 green guys have to be the same for there to be a limit. So we don't know exactly what that is, but we get. How about f of 1? How do I figure out what f of 1 is? So yeah, it's going to be ax plus, it's going to be the middle one, right? Because that's equal to 1. So it's going to end up being a plus b. Okay. I could figure out if it was just A or B, I could figure out, but I have an A and a B, so I can't figure it out. But what I can figure out is I can set up an equation, right? I can set up an equation. A plus B equals 2. I'm going to put that equation to the side because I'm not done because I also have to check another number, right? I also have to check 2. So I'm going to put that one to that's as best as I can do right now. That's as best as I can do so far. So now I'm going to do the same thing for 2 because I know 2, there could be some issues with continuity. Okay, so let's do the same thing for 2. The limit as x approaches 2 from the left for f of x. The limit as x approaches 2 from the right, f of x. The limit as x approaches 2 overall, and f of 2. Okay. So if we wanted to check the limit as x approaches 2 from the left side, the less than side, which one would we use? Top, middle, or bottom? The middle, right? The middle, because that's where it's less than 2. So I'm going to plug in 2 for x. When I do that, I get 2a plus b. I get 2a plus b. Okay. Now I want to check from the right side. Which one am I going to use for that one? The bottom, 3x, right? 3x. So I'm going to plug in x to the bottom. 3 times 2 is 6. The overall limit, well, the overall limit has to equal both of those green guys, and they don't equal each other right now, so I'm not worried about the overall limit right now. F of 2. What is f of 2? How do I figure out what f of 2 is? Bottom. We're going to use the bottom because that's where it's equal to 2, right? So it would be 6. So this is kind of the same deal as the last one, right? The best I can do is say 2a plus b equals 6. That's the best I can do right now, right? This is what I'm going to do now. I have to figure out what a is equal to and what b is equal to. So I have two equations. They're two linear equations because there's no squareds or anything. So what I'm going to do is I'm going to set up, it's called a system of solving systems of equations. Systems means more than one equation. There's 3 ways to solve systems. You probably did this in junior high or definitely Math 1, but we haven't done it since. 3 ways of solving systems. You can graph them. I don't want to graph them. I can't use a calculator on this, so graphing, no. You can use what's called substitution, or you can use what's called elimination. Doesn't matter. I'm going to use elimination because that's the way I prefer. And I'll show you. I'll show you what I'm going to do right now. So let me get another sheet. Okay, so I'm going to take those two guys. A plus B equals 2. And 2A plus B equals 2. 6, sorry. There we go. Okay. Let me go down here where I have some more room. I don't want to do that. Yeah, it might be a little confusing, but oh well. Okay. So I have A plus B equals 2. And I have 2A plus B equals 6, right? That's what I ended with. That's the best I could do. So what elimination says is if you have the same variables on top and bottom and they're linear, you can eliminate one of them using addition or subtraction. So if I was to add straight down right now, would A or B eliminate? Would A or B go away? No, I'd have 3A and 2B, right? So what I have to do is I want to be able to add straight down and one of them go away. So what I'm going to have to do is I'm going to have to manipulate them a little bit, change them a little bit. The B's would cancel out. How would the B's cancel out if one of them was a negative, right? So what I'm going to do is I'm going to multiply the top equation by -1. I can do this because I'm doing everything by -1, not just B. So I'm multiplying everything times -1. So it becomes -A minus B equals -2. Those two are actually exactly the same. One is just multiplied by -1, one isn't. So I haven't changed it, I just manipulated it so it looks a little different. The bottom one I don't need to change, because now when I add straight down, the B's eliminate. And I have 1A equals 4. You've done this before, trust me. You've done it. You might not remember it because you've done it years ago, but you've done this before. It's called systems of equations. Okay? It's actually a Math 1 standard. So this, what I'm doing is math 1. It might seem a little out there because you just haven't seen it in a while, but it's what we did in math 1. So now that I know A is 4, what does B have to be? So if A is 4, what does B have to be? -2. -2. B has to be -2 for it to work. And that's how you figure it out. You just plug it into one of them. So A is 4, B is -2. You have to set up two equations and do it that way. If you're solving for two unknowns. If you're only solving for one unknown, you don't need to do this. But if you're solving for two unknowns, you got to do it this way. Okay? All right, I want to give you a problem like that on your own. I'm not going to do two unknowns, but I'll do one unknown. Okay, so when you plug in 7, so from the left, we're going to use the top, right? When you plug in 7, what happens? You get 0 over 0, right? You don't get 0, 0? Let's see. We get 7 squared minus 2 times 7 minus 8 over 7 squared minus 5 times 7 minus 14. So we get 49 minus 14 minus 8, 49 minus 35 minus 14. So yeah, what do we get? We get 0 on bottom, and we get 27? Okay. So what does that mean when we get 0 on bottom and a number on top? So that means we can't do anything else. We can't factor it. You can try to factor it, but it won't factor. Like the top will be, that's what I was thinking at first. I'm like, maybe we can factor the top. The top will be x plus 2, x minus 4. And then the bottom would be x minus 7, x plus 2. These would factor, but still, if I plug in 7, it would still give me 0 on the bottom, right? It would still give me 0 on the bottom. So because of that, that means there's an asymptote at 7. There's an asymptote at 7. That means there's a vertical asymptote at 7. It means I can't make this continuous for anything. So we would say there are no values that for k, there are no values for k that would make f of x continuous. Because there's a vertical asymptote at 7. Because even when I factored it, I still had an x minus 7 on the bottom. That's why I said it was a little bit of a trick. This one was a little bit of a tricky answer. It's not tricky in your work. You did the same thing, but the answer was a little different. Okay. All right, let me give you one more like that, a more normal one like that. Let's try this. Kx squared when x is greater than 2, kx plus 16 when x is less than or equal to 2. This one will have a solution. This one will have k. You'll get k. Okay. So 2 is the only spot where k could be or continuity could be an issue. So 2 from the left, I plugged in the bottom. So that's 2k plus 16. 2, the limit as x approaches 2 from the right, I plugged into the top. That's 4k because it's 2 squared. The overall limit will be both of those equal to each other. And then the last one, I would use the bottom because that's where it's equal to 2. So I get 2k plus 16 equal 4k. Set them equal to each other. Solve for k. Get k's on the same side. So divide by 2, you get 8. K have to be 8 to make it true. Okay. All right. Okay, so there's one last thing we have to talk about in this chapter, and it's tiny. The idea is really easy, but sometimes it looks a little difficult. It looks a little more difficult than it is. So that's called the intermediate value theorem. The intermediate value theorem. Okay, so the intermediate value theorem. This is the textbook definition of it, but I'll explain what it is. So I'm standing over here. Imagine if I drew a line, straight line, like I got some tape and drew a line from here on the ground all the way to the window. So let's say I got some blue tape and I drew a line all the way there, right? So there's a line on the ground. And I'm over here, right? I'm over here. And let's say you leave class and come back in. And now I'm over here. What had to have happened? What had to have happened? You might not have seen it, but what had to have happened? So I start over here. You walk outside for a second. Come back. I'm over here now. What had to have happened? I had to have moved. Keep going. That's right. Think about the line. What had to I have done? I have to have crossed the line somewhere. Do I know when I crossed the line? Do I know what time, exactly when? No, I don't. But I had to have crossed the line. It's like a river. I think about it like a river. If 1 minute you're on this side, and the next minute you're over here, or later on you're over here, what had to have happened? You had to have crossed the river at some time, right? Do we know where or when? No, but we just know you had to have crossed the river. That's what the intermediate value theorem says. The intermediate value theorem says if I'm at A, and then later on down the road, I'm at B, I had to have crossed over the line sometime. Do I know when? Do I know how many times? Like if you walked outside for a minute, I could have gone once, twice, 3 times. I could have crossed it a number of times, right? But I had to have crossed it at least once. That's what the intermediate value theorem says. So it's kind of an assumption. We assume that it did because there's no other way for me to get it from here over there without crossing the blue line. Okay? So how do we show it? Where are you at A? What's your y value at A? What's your y value at B? If this line is at 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 5.5, right? This line is at 5.5. If here I'm at 2.1, and over here at B, I'm at 7.2, that means I had to have crossed the line at 5.5. I had to have, right? That's what it says. That's what the intermediate value theorem says. That's what that says, right? As long as it's continuous, as long as my function is continuous, I had to have crossed the line. Okay? So let's look at Probably won't finish this. We'll finish it early, but I want to do at least 1 or 2 problems because the idea is not hard. Sometimes it looks harder than it is. The questioning looks harder than it is, but it's really not hard. Okay, so explain in words why the function has a 0. So tell me about a graph. How do you know a graph? How do you know a function has a 0 when what happens? Let me draw a graph. How many zeros does that graph have? 3. Yeah, how do we know? Because it crosses the x-axis, right? So that's what this is asking. Do we know that from 0 to 1, it crossed the x-axis? What we have to do is show where did it start and where did it end, right? So it started at 0. So let's find the y value at 0. How are we going to find the y value at 0? Plug it in. So let's plug in 0, right? 0 cubed plus 3 times 0 minus 2. So at 0, when x was 0, y is -2. Is that above or below the x-axis? Below. So now let's plug in 1. What happened at 1? One plus 3 minus 2. 2, right? Positive 2. So the y value at 1 is positive 2. So did it cross the x-axis? How many times did it cross? We don't know. We don't know. I don't care. All it's asking is, does it have at least one time crossing? Yeah, it does. There's no way for me to get below the x-axis to above the x-axis with having outcrossed it, right? So explain in words why the function has a 0. By intermediate value theorem. IVT. IVT, you could just say by intermediate value theorem. It has to, because you can't start below the x-axis and then go above the x-axis without crossing over the x-axis, right? How many times did it? I don't know how many times. Once, twice, 3 times, but it did it at least once. Okay, so let's look at number 2 now. From 0 to pi. From 0 to pi. Well, let's check out where it is at 0. Zero squared is 0 minus 0. What is cosine of 0? It's not 0. It's 1. Yeah, it's 1. So we get -1. Is that above or below the x-axis? Below. Slightly below, but it is below. Now let's check at pi. Pi squared minus pi minus cosine of pi. Now, I'm not concerned about the actual number. I'm just concerned whether it's positive or negative. Is it above the x-axis or below the x-axis? So pi squared minus pi. What is cosine at pi? Is it -1? Is it? Yeah, you're probably right. Let's see. Yep, -1. So minus a -1. So if I were to take pi squared and subtract a pi and then add 1, would that number be positive or negative? Well, think about it. Yeah, think about it. Pi is around a little over 3, right? So if I square it, it becomes about 9. And then I take away 3. And then I add 1. That's a positive number. So yeah, it started out below and then it went positive. So now it's it had to have crossed at least once. At least once. Okay, we're going to stop there. We're going to do one more. We're going to do a couple more problems. I'm going to give you that one and I'll do one more and then we'll be done. The rest of the time, so notes wise, we're going to maybe 10-minute notes, not long. The rest of the time, I'm going to give you to start on your assignment. I have an assignment based on this. So I'm going to give you, that's all we're going to do. Okay, finish up the notes for a little bit and then we'll be done. Okay, that's the last thing we're going to do, intermediate value theorem. These problems look